we'll keep going then with talking about inverse functions and one-to-one functions. Finish that up today. So last time we talked about what it means to be one-to-one. Graphically, if you have a graph of a function, how do you check whether or not it's one-to-one? Yeah, horizontal line test, right? Remember that horizontal line test says that if you cross in more than one spot, that it's not one-to-one. Because again, that shows you that you have at least two inputs that give you the same output. You're at the same height. Okay? So horizontal line test is a graphical way to check if a function is one-to-one. We had another line test. What was the other line test we had? Vertical line test. What was that used for? Yeah, determine if it is a function, right? So make sure you keep them separate, right? Vertical line test just says whether or not something is a function. Horizontal line test says you already have a function. You're checking whether or not it has an inverse, right? Whether or not it's one-to-one. So then we spent some time talking about finding inverses. So let's do another example of that. We'll have some practice problems here at the end of class today as well. So here is a function. We've got a 4x plus 2 over a 3x minus 6. This is an example of a specific type of function that's referred to as a rational function. You've got a polynomial, a linear function on top. You also have a polynomial on bottom. So that particular type of function is called a rational function. We'll investigate rational functions later in the semester. Actually, in the next chapter, I believe. Or maybe later in this chapter. One of the two. Anyway, not worried about that right this second. We're just worried about finding its inverse. Well, if I wanted to check that it's one-to-one before I even start, I would need to get a graph of it. Now, if you don't have a graphing calculator, there's a nice program online. You may be familiar with it, but I want to go ahead and show it to you anyway, in case you're not familiar with it, because it's a nice graphing calculator application. There's also they also make an app for your phone. It's called Desmos, D-E-S-M-O-S. So if you go to desmos.com or search for Desmos on App Store or Google Play Store, either or. It's a free app, so it's not like you're not paying anything for it. It's a nice graphing calculator. So again, of course I forgot what the name of my function is. Handouts here, so. There it is. So if I do 4x plus 2, notice that if I try to do a fraction there, it wants to make a fraction, but it's not doing it correctly. So I actually need parentheses around that 4x plus 2, and then make a fraction. 3x minus 6. There's a nice quick graph of the function. So again, if you don't have a graphing calculator, but you're working on something on WebAssign or looking for practice of things and want to get a quick graph, Desmos is a great resource for doing that. Looking at this graph, does this pass the horizontal line test? If you take any horizontal line, does it only cross one time? No. Looks like it, right? Because notice that even on here, I've got little grid marks on there. It says, hey, you've been putting in some horizontal lines for you, right? I'm not hitting this graph more than once anywhere. So this is one-to-one, so it does have an inverse. Okay? Again, I just wanted to do that real quick in case you wanted to do something graphically. And this is a wonderful graphing calculator site, app, if you want to put it on your phone. It works really, really well. All right, anyway, you seem all super excited about that, so I'll continue. All right, so let's see. We know now that it did pass the horizontal line test. It is one-to-one, so we can find its inverse function. What's our first step? Yeah, x's to y's and vice versa, right? So again, we equate our f of x with y, and then we flip around everything that is an y becomes an x, which there should only be one y, right? It's a function. There should only be one thing that says y, the y equals part. and then convert all of your x's to y's. So we get the equation x equals 4y plus 2 over 3y minus 6. And again, after we do this, we want to solve for y, right? What do you think we might want to do first? Do you like that fraction? No. Would you like to get rid of the fraction? Yes. How can you get rid of the fraction? Yeah, let's multiply both sides by the 3y minus 6, right? Get rid of your fraction. Sounds like a good plan to me. So we'll get x times 3y minus 6 equals 4y plus 2. We're just declaring the fraction there. Now again here, our goal is to solve for y. Isolate the y. What that means is that you can only have y on one side. You have to have y equals something with absolutely no y's in it. Okay? It does not mean have a y on one side and have a y on the other. That's not solving for y. Okay? You cannot have y's on both sides of the equation and say, I solved for y. That doesn't work. Okay? You have to have y equals something without y's in it. Okay? Right now I've got y's on both sides. So I have to get my y's on one side. Before I do that, what should I do with that x? Distribute it. Good. Distribute it. 3xy minus 6x equals 4y plus 2. Okay? I know. It's very tempting to subtract 2 and divide by 4 and say, I solved for y. That's not solving for y. What's wrong with that? There's a y on the other side, right? You have to get all of your y's on one side. Okay? So move everything with a y in it on one side, everything without a y in it on the other. Okay? So in this case, we'll subtract the 4y and we'll add the 6x. Okay? Move everything with a y to one side, everything without a y to the other. Remember again, we're trying to isolate the y. Okay? I want to put the y's together, not keep them apart. All right? All right? Now, why do I do that? What do you notice is in both terms on the left-hand side? Oh, yeah. A y. What can you do? Take out the y. I can factor it out. Good. I can factor out the common factor of y. And now to isolate your y, to solve for your y, what should you do to both sides? Divide by the 3x minus 4. Yeah, exactly. Now that we've solved for y, that is our inverse function. So you get your inverse function here is 6x plus 2 over 3x minus 4. What's that? Yeah, the 6 is the 4 6 places. Yep, that's exactly right. Yep. That one okay? Okay. Now again, there's not anything that I find as this is the end-all, be-all type of inverse function problem, but I guarantee you will see one of these on a quiz, and you will see one of these on the next test. Okay, so make sure you understand how to do this inverse problem specifically like this. Okay? The reason is because this skill of moving all your y's over to one side and everything else to the other and being able to factor out does pop up later on in this class and other classes. Okay? That's why I do this particular type of thing. All right, so let's continue. hit scroll. There we go. All right, so what does it look like when you graph one of these inverse type of functions? So let's look at a specific example here, and then we'll talk about just creating a graph of an inverse from the graph that we're given, and then we'll verify this one with actually finding the inverse. Okay. So, pardon me. We've got the equation here, y equals 4x plus 1. So that's a nice linear function. Crosses the y-axis at 1, has a y-intercept of 1, slope of 4. Okay. So what does it mean to graph an inverse function? Well, let's remember what we do when we find an inverse function. Remember, we flip-flop the x and the y around, right? So graphically, what does that mean? This is the point 0, 1. If I flip-flop x's and y's, what point does that become? 1, 0, right? I'll put that over here, okay? This point up here, what point is that? It's the other way around though, right? It's 1, 5. That one's the point 1, 5, right? If I plug in 1 for x, I definitely get out 5 for y, don't I? Up here. If I flip-flop it, I get the point 5, 1. Now let's just play connect the dots here. That's what the inverse is going to look like. So this would be your graph of your inverse function. Notice that the inverse function and the original function really are mirror images of each other. Not quite, but if you take and reflect around the line y equals x, you get the graph of the inverse function. Like I said, let's verify that we really do have a graph of our inverse function, or at least a sketch. If I go back up here to this function and ask you to find the inverse, what do we do first? Flips x's and y's. And then solve for y. What do we need to do to solve for y?
Flip the x's and y's.
I did that. Did that. Take away the 1. And then divide everything by 4.
X minus 1 over 4.
Yep. And I'll go ahead and just, you get x minus 1 over y, over 4 equals y. I can distribute the 1/4. I can write it as y equals 1/4 x minus a 4th. This was the inverse, right? Does the graph we just came up with look like that line? Does it look like it has a slope of 1/4? Yeah, Josiah.
Yeah. Would it be? I don't know. I'm just like, I keep getting confused about the form of it. Mm-hmm. So would it be fine if I put it as x minus 1 over 4?
Yeah, that's okay. Yeah, but I just wrote it this way. I just wrote it this way so that we could see the line, right? Okay. So this would be a line with a slope of what? 1/4 and a y-intercept of negative 1/4. Good, right? Does this look like it has a slope of 1/4? If you go from this point here, which was 1, 0, to this point here, which is 5, 1, we go right 4 and up 1. That's a slope of 1/4, isn't it? Does it look like we crossed the y-axis at negative 1/4? Yeah. So again, if you want to get the graph of the inverse function, to summarize this, we start with the graph of y equals f of x, and we reflect the graph, across the line y equals x. Remember we did transformations where we reflected across the x-axis or reflected across the y-axis. For inverse functions to get the graph, we reflect across that diagonal. And again, the reason is because we're flip-flopping what x and y means, right? Y's become x's, x's And also, by the way, we talked about horizontal line test as checking if something is 1-to-1. What happens if I have a horizontal line? Say I have the horizontal line y equals 2, and I ask you to reflect that about y equals x, or flip-flop your x's and y's. What kind of a line do you end up with if I flip-flop x and y? Instead of y equals 2, we get, I just change out x's and y's. Instead of y equals 2, you get x equals 2. What kind of a line do I get? Vertical. Notice that when you reflect a horizontal line, you get a vertical line. So really what the horizontal line test is doing is it's checking whether when you do that reflection, you get a function. It's really just the vertical line test to discuss. So again, the important part of this is, at least from our perspective, the important part of this is to get a graph of the inverse function, start with your original graph, and flip it about the line y equals x. Okay. Let me go back over to Desmos real quick and do the inverse, the graph that inverse of the function we just did a minute ago. Bless you. So here was that original function, the 4x plus 2 over 3x minus 6. The inverse was what? It was 6x plus 2, if I could type, divided by 3x minus 4. Is that what it was? Okay. Let me draw the line y equals x in here. It's not a great picture, but notice that if you flip the red one here, it's going to become that blue one. We see that nice symmetry there about that green line. It's a little harder to see with that one. That one's not particularly interesting. Let's do the one we just did and make it maybe a little bit better picture that I just drew. We had 4x minus 1. And then the other one was 1/4 x minus 1/4. It was 4 plus 1, wasn't it? Sorry. There we go. Yep, there it is. I knew something was wrong. But notice here was the original line, is that purplish blue line there. Here's the black line, is the inverse function. The green is your y equals x. Notice that it really does, if you tilt your head sideways a little bit, I guess, diagonally, you really do see that reflection across that line. All right. Anyway, let's go back to what we were doing here. Maybe. Here we go. All right. I mentioned this a little bit on Friday, but this is an important concept when we start talking about doing inverses of functions that aren't 1-to-1. Here's the graph of y equals x squared. F of x equals x squared. Got that nice U-shaped parabola. But certainly, I think we can all agree that this is not 1-to-1, right? This definitely, absolutely does not pass the horizontal line test, right? But squaring is something that you want to undo. What undoes squaring?
Rooting.
The square rooting, right? So we already talked about undoing squaring by doing a square root, right? So somehow we must be talking about what the inverse of the squaring function is. So when we do the inverse, we have to talk about making sure we restrict where we actually take the inverse. And we talked a little bit about this last time. But what we do is I want to pick a piece. I'll write this off to the side. We want a part of the function that satisfies two things. The first thing we want to make sure is that it's 1-to-1. We cannot talk about an inverse being a function without the function being 1-to-1. Okay? So we already know that this is bad. Okay? So I want to cut this thing up. I want a piece of this function that's one-to-one. Well, there's lots of options, right? I could do that little bit if I ignore everything else. That's certainly one-to-one, right? Or I could do a little bit over here. That's one-to-one. I can't do that. That's not one-to-one, right? But I could cut a little piece over here. I could cut a little piece over here. But that doesn't undo everything that I want, right? The range of my function here is 0 to infinity, isn't it? I want to be able to take the square root. I want to undo the squaring function of anything that I could possibly get out, right? I don't want to say I can't do the square root of 9 because I didn't account for 9, right? I want to make sure I account for everything in the range. So the second thing that you want to make sure you do is make sure that everything in the range is accounted for. Again, the square root function wouldn't do me any good if I couldn't do the square root of 9 or the square root of 25, right? If I cut my range off too short, I can't undo everything. So those are the two conditions that I want to make sure are satisfied. How many pieces can you cut up this graph and satisfy both of those conditions? One-to-one and taking up the entire range. How many pieces can you cut that into? 2, right? I could look at the right half of the parabola, or I could look at the left half of the parabola, right? Okay. Think about when you solve equations by doing the square root. Anytime you do the square root of both sides of an equation, what do you always have to make sure you do? If I had x squared equals 4, and you did the square root of both sides, what are the answers? Plus or minus 2, right? Or if you think about your quadratic formula, it's negative b plus or minus square root of e squared minus 4ac, right? There's that plus or minus piece in there, correct? That comes from the two pieces that you can cut the square root function, or the squaring function into, and be one-to-one and encompass the range. One's going to be your positive square root, one's going to be your negative square root when you do the inverse. Okay? So, we make a choice. Whenever you restrict the domain, you make a choice. So when you define the square root function, we choose to ignore this side. We cut that part off. Okay? And only look at this side here. Okay? So to define the square root function, we restrict the domain of y equals x squared to 0 to infinity and take the inverse. Now, remember, square root is also something we've already looked at the graph of. Square root looks like that, right? Starts at 0, 0 and goes up and to the right, but slowly. When you do your square root function here, I'll draw it in red. Maybe I'll draw it in green. When you do your square root function here, notice it goes like so. And it is that reflection about the line y equals x again. But anytime that you've got a function that's not one-to-one, but you would like to be able to take its inverse, you've got to restrict the domain first. Okay? This is a very big deal in trigonometry, for example. Okay? But anyway, that's what we were talking about, restricting the domain. All right, so let's see if we can do this for this function, f of x equals 3 times x plus 4 squared minus 5. All right, so This says using an appropriate domain restriction, find the inverse. Let's just see if we did this blindly and see what the problem pops up, and then talk about what the domain restriction has to be. Okay? All right, if we were not worried, if we didn't check first that this wasn't one-to-one, the first thing you would do is what?
Swap the y and the x.
Swap the y and the x. Good. That's exactly what we do. So again, if I equate my f of x with y, first step would be swap your x's and y's around. All right? That'd be first step. Yeah? Okay. Forgot my squared. We would need to add 5, right? So far, no issues. Right? Nothing wrong with adding 5. I have no issues undoing adding 5 or subtracting 5. I just add. Next step would be to
Multiply by 3.
divide by 3. Yep. I'm going to reverse my order here of my fraction, or my equation. Next step would be to divide by 3. Again, no issues, right? So far, so good? No issues at all? Okay. What would be the next step?
Take the root.
Take the root. That's where the issue is going to pop up for the first time, right? Right? And again, when you take the square root of both sides, you always get plus or minus, right? So it's the squaring here. At this point, we get a problem. Okay? When we take the square root, we would get, plus or minus, I'll write it as square root of x plus 5 over 3 on the right. Now, what's wrong with that? Remember, we want an inverse that is a function, right? In order to be a function, when you plug one thing in, how many things are you allowed to get out? 1. If I plug one thing in here, how many things do I get out? 2, right? That's bad, right? For functions, you're not allowed to plug one thing in and get 2 things out, okay? So this is what's telling us. This tells us we need to restrict. All right. Doesn't tell us where to restrict to, right? It just tells us that we need to restrict. Right? Okay. So let's go back up to this original function. Now let's think about your transformations. We've got several transformations here, right? We did transformations in graphs before. What did that 3 do?
Stretch it
Stretch it vertically, right? But did we have any trouble undoing the 3? No. What did the minus 5 do?
It shifted it down 5.
Shifted it down 5, and did we have any problem undoing that? No. Okay. How about that plus 4? That's on the inside. What does the plus 4 do? Left 4, right? And this is where we were having the issue of where to undo, right? It's inside that squaring.
Yeah.
Correct? All right. What shifted left 4? Let's think about your graph. Here's the original graph, right? This is where that problem occurred, isn't it? Right at the bottom?
Yeah.
Think about when you shift it left 4. Now the bottom is over here. I didn't do up or down or anything. Shifting it left 4, the bottom is here, isn't it? Yeah. So where do you think we might want to start restricting our x's at? -4, where we shifted to the left, right? Okay? Now again, just like when you did your square root function a minute ago, we said that we could restrict the squaring function either to the right of 0 or to the left of 0. Right? One or the other? We can do the same thing here. We can restrict to the left of -4 or the right of -4. If you restrict to the right of -4, do you think you would use the positive or do you think you would use the negative? If I wanted to restrict to the right-hand side or the positive side of -4, do you think you'd use the positive or the negative? Positive. If I restrict to the left-hand side or the negative side, which one would you use? The negative. Yeah. So in this case, if we restrict to x being greater than or equal to -4, then our inverse function becomes y plus 4 equals positive square root of x plus 5 over 3. And we can finish it off by subtracting 4. But notice what told us about the restriction. What was in here, right? What was inside the function. The 3, no issues undoing this multiplication by 3. The -5, no issues there because those are on the outside of the function, right? It was what was on the inside of the function that was causing issues. So that's where we needed to worry about the inverse, the restriction part. All right. In particular, when you've got these squaring functions, you're going to have a left branch or a right branch, and you'll have to worry about the restrictions. And that's where this thing is bottoming out. And in the next section, that Hope's actually going to do tomorrow, or Wednesday. Hope's going to teach on Wednesday. You're going to look at how do you figure out where that bottom part is by looking at the graph, or looking at the function, I mean. So we'll talk more about that next time as well. All right. Pardon me. Any questions on why we had to restrict here? That's the important part. Do you understand why we have to make a restriction? Okay. Because we've got a non-one-to-one function. So we've got to break a piece out of it out. All right. Pardon me. So this last part here is just summarizing why we care about inverse functions. The whole point of doing all of this stuff is to undo what an original function does. Okay? Inputs become outputs. Outputs become inputs. That's the whole point, right? Okay? So if inputs become outputs and vice versa, the domain refers to what for the original function? Input or output? Domain refers to inputs, right? Domain is what goes in. Range is what comes out, right? Okay. So what goes into the original function has to come out of the inverse, right? So if the domain of the original is A, the range of your inverse must be A. What goes into the original comes out of the inverse. Okay? And vice versa. This, is that an in or an out for the original? Out, right? Range is outputs, right? The outputs of the original become the inputs of the inverse. So again, this just means, I'm just going to write it in words over here to the side. Inputs of the original are the outputs of the inverse, and vice versa. Outputs of the original are the inputs of the inverse. Inverses interchange roles of x and y, and that's exactly how we found the inverses, right? Flip-flop your x's and y's, right? That's what they do. And again, the important part, the other important part of inverses or the real important part maybe is a better way to say it, inverses and functions, original functions, have to undo each other. Meaning when you compose them, you get back to where you started. Right? If you put your shoes on when you leave the house in the morning, you come back home, you undo that process, you take your shoes off, you're left with your feet bare again, right? You still have the same feet, didn't change your feet, right? Feet go into the shoes when you leave, feet come out of your shoes when you get home. That's doing the composition, right? So if I start with X, apply the function, and then undo the function, what should I end up with? If I start with X, do the function, undo the function, what should I end up with? X. Right. Good. Right. Okay. And it should work the other way around too. If I undo the function and then do the function, I should end up back with X again. Okay. Now the only thing I have to be worried about is making sure that your X can go in the right places. Okay. Right. Looking at this part here, where does X go in first? Does it go into the inverse function first or the original function first? The original, right? So this is provided that your X is in the domain. Oops. Of f of X. If it's not in the domain, you can't do it. So what I mean by that is, if your original function were the square root of X, you couldn't put negative numbers in it. Does that make sense? Okay. Where does this X go? Here in the second one. Yeah, in the domain of the inverse, which is the same thing as what for the original. The domain of the inverse is the same thing as the range. Good. So this is provided that X is in the range of the original. Good. Again, this property here is the whole point of doing inverses, right? You're trying to undo whatever the original function did. So if the original function was the squaring function, you want to do the square root function. If the original function was the cubing function, you did cube root it, right? All those things. Okay? That's the whole point of being an inverse. You're trying to undo whatever you did. Right? Right? Trying to undo whatever it did. So if it undoes what the function did, you should end up back to where you started. Okay? I drive to the store and then I drive back home, that undoes what I did, right? So if I compose driving to the store and back, I end up where I started. That's the same concept here, right? Do the function, undo. This last part is just making sure it makes sense for where you started, right? If I want to undo driving from home to the store, then I better have been home to start with, right? Okay. All right. So let's look at these other answers, or the other examples here, and then we'll have some practice problems. Well, at least we're working on towards the end of class here. All right. The function, you put in 5 and you got negative 2 out. Okay? This says undo that process. So if I want to undo the process, what do you end up with at the end? 5. It undoes, flips it around, right? Again, this is just an illustration of inputs become outputs, outputs become inputs, right? Input of the original, output of the original. Input of the inverse, output of the inverse. Okay? So what's the next answer then going to be for the next blank? Be a 3, won't it? The inverse takes 3 and gets out 6. So the original must have put in 6 and got out 3. Does that make sense? Okay. All right. This last one, before we go to showing that they're inverses of each other. Does this 7, the way this is written, does this 7 refer to it in terms of the original function? Does that 7 refer to an input of the original function or an output of the original function?
Output.
It's an output, right? Because it's an input for the inverse, so it's an output for the original, right? So what this is actually asking you to do is solve an equation. This says if the output is 7, what was the input? Can you figure that out? If you got 7 out of the function, can you figure out what you put in? Well, how did you figure that out?
I created the inverse by switching the y and x. I mean, it would have been easier as just putting it as 7 equals 3x minus 2.
There we go. Yeah. So in this case, we know the output is supposed to be 7. And figure out the input. Can you solve that for x? Not too bad to solve it for x, is it? Add 2 and divide. So again, this is just asking us for an equation to solve. We know the output was 7. The input associated with that must be 3. We just solve the equation. All right. Let's do this last one here to illustrate the inverse idea. Remember, to show that they're inverses of each other, we're going to show that when you compose them, you get back to where we started. So if they are inverses, then what must be the case when we do F composed with G? If they're inverses of each other, what must we get when we end up? What must we end up with when we're done? X, yeah. If we did it the other way around, and did G compose with F of X, what must we end up with when we're done? It's still X, yeah, good. Remember that if they are inverses of each other, then we have to get back to where we started, no matter which order we do it in. Okay? If they're inverses of each other, you have to get back to where you started no matter what. Okay? All right. With the shoe example, if you start by putting your shoes on and then taking your shoes back off again, you end with your feet. Right? If you started with shoes on, take them off and put them back on again, you end up with shoed feet. Right? Okay. So let's talk about composing these two things. So if we want to do F of G of X, that's F of 1 over X plus 2 and then minus a 1. What do we do with this again? What does that say it told us to do? Yeah, we put it in for X, right? That's just our composition, isn't it? Oops. So, do this again. 1 over X plus 2 minus 1 plus 1 minus 2. This was our X right here, isn't it? Remember, composition means take out the X and put in literally what you see in the parentheses. Right? So we take out the X and put in 1 over X plus 2 minus 1. What happens in the denominator there? What happens in the denominator? The 1's cancel, don't they? We got 1 over X plus 2 minus 2. We're dividing by a fraction. That's what this says, isn't it? 1 over 1 over x plus 2 just becomes what?
1 over x plus 2.
Careful. When you divide by a fraction, you multiply by the reciprocal, right? So what does that become? What is this basically says take the reciprocal of x plus 2. What do you end up with?
1 over x plus 2.
It's not 1 over anymore. It's just x plus 2, right? It's be x plus 2 over 1, right?
I said x plus 2.
I thought you said 1 over x. I'm sorry. And then minus 2 on the end. And what do we end up with? X. Okay. It should work the other way around too. If you do g of 1 over x plus 2 minus 1, oops, sorry, x plus 1 minus 2, I put the wrong thing in. So the 1 over the f of x goes in for the x, in for g, right? So we're going to take out this x and put in this expression. So we have 1 over x plus 1 minus 2, and then a plus 2 on the end. What happens with the 2's? They cancel out. This looks a lot like the previous part, doesn't it? Now this part is x plus 1 minus a 1, and you end up with x at the end. So if a problem asks you to show that things are inverses of each other, it tells you to compose those two things and show that you rarely do get x. So to finish this off here at the bottom of your sheet, x squared and square root of x, are those inverses of each other? When you do squaring and take the square root of those inverses of each other. So these two blanks here should both be filled in with what?
X.
It should be x in both of them, right? Because they're undoing each other, right? So both of those blanks are x. The other part is asking you about domain pieces. Okay, so let's look at this. Here, where does this x go into in the first part? Where does this x go into? Does it go into the squaring first or the square root first?
Square root.
The square root, right? So what has to be true about this x if it's going to go into the square root?
X has to equal weight.
What can't it be?
0.
And 0 is okay, but what can it be? Negative numbers, right? I can't put it in negative. So in that first case, it only works if x is non-negative, if x is greater than or equal to 0. However, in the second case, any issues plugging in an x here? No, because it goes into the x squared. Once you square it, because it becomes positive, right? So is there any issues with taking a square root? No. So the second one works for all x. Don't have any issues at all. I know it got a little weird at the end, and that's okay. Take a little time to get used to it. Here's some extra practice problems for you. And I'll post an answer to these on Google as well that go over these types of things. So you have some extra ones here. Oops. All right. All right. So again, on Wednesday, Wednesday, Hope's going to teach over section 3.1, which talks about quadratic functions. On Friday, we'll get into some new stuff as well, but on Friday, we'll do a quiz over inverse functions. Okay? Friday, quiz over inverse functions, section 2.8. Okay? All right, have a good one. We'll see you on Wednesday.